Thank you for having me today. So as Reza said, I'm going to talk about our work on AI and specifically infrastructure for self-driving cars at Nvidia. And then I'll segue into a library and framework we recently released that's called Rapids. Was super excited about it. But before I dive in, I just got the news this morning, and I'd like to give a warm applause to these three pioneers. I'm super excited to hear that news. I did my PhD with Jan LeCun a few years ago, and I think it's a great recognition of the pioneering work these guys have done. So let's congratulate them. All right, so at Nvidia, we've been working on self-driving car technology for quite a few years now. One thing about self-driving car tech is that there's such a gap between a cool demo and something that actually goes all the way to production. And so, in a nutshell, building AI for self-driving cars is incredibly challenging. And the question is why? So I think there's three main reasons why that's the case. The first one is the sheer number of perception modules and components you actually have to assemble to essentially build a full representation of what surrounds the car to actually safely actuate in the world. So you see a sample of those types of perception modules below. The videos we're showing here are coming from our perception stack. So there's like 20, 25, 30 such modules, and they each need to be built with the same degree of quality and safety verification. The second thing is the diversity of scenarios, road conditions, weather conditions, geolocations that you're going to have to cover to actually safely deliver a product that works. So we're showing a few of these up there, so from lighting conditions to weather types, the list of the size of the space that you have to cover and actually prove that the stack you're developing works correctly in is tremendous. And the third thing is really validation. You get to a point where you have a good, solid demo that showcases the base functionality, so perception and actuating in a set of initial scenarios fairly quickly. And then it's really going to be about going down that very long tail of rare events, and you're going to have to prove that you can actually perceive objects and lanes and traffic lights for millions of miles without any failures. So what scale are we talking about exactly? So I think it's really, looking at this graph really gives you a sense of the scale of the problem and why the data aspect of it is so critical. I think there's really two aspects. There's testing data and training data. For testing data, if you think and start from first principles, and you look at the typical accident rates in the US, and you want to be able to exceed that, we're rapidly talking about proving that all the perception components you're building are essentially having the right behavior on more than a few million of miles. So that gives you the scale of the data. That times the dimensionality of the sensor platform we're talking about, multiple cameras, typically 10, 12, 15 cameras surrounding the car, plus potentially multiple LiDARs, radars. All these sensors really add up. And so if you talk about millions of miles, you essentially talk about hundreds of petabytes of data that you're going to have to collect over time to build up test scenarios and validate your whole perception stack. So tremendous scale. And then, of course, on the training data side of things, we basically have no idea how much data we really need. What we know is that we can define targets in terms of our failure rate and how far we want to push the quality of our perception stack. But we do not know how much training data we're going to have to pile up to actually achieve these goals. So today at Nvidia, we're already dealing with quite a bit of scale, and this really makes our work on all of this really challenging. On the left side, I'm showing the typical data size that we're collecting on our current sensor platform. So we're typically talking about a few petabytes of data a month being ingested from all our cars. Each car typically has 12 cameras, so that's what's really driving the data volume. We're currently handling a set of 15 petabytes of data for testing and training purposes. So moving this around is really a tremendous problem. And then the second column shows you what we actually have to do on that data. So the data itself is raw. And of course, we still haven't solved the true AI problem of going from that data and solving the entire problem of self-driving car through imitation learning alone, although it's something we're invested in. And so there's a lot of labeling we actually have to go through to augment the data and give us all the symbols we need. So we're currently employing 1,500 labelers to actually help us go through tens of millions of objects labeled a month. And really the challenge is not just the volume and scale, but all of this has to be relevant. It has to be the right data for the right tasks at the right moment in the life cycle of the project. Once you have data, labels, obviously all of this needs to get to compute, and you have to start using that for training and testing. And so the last side of things is our GPU farm, which is today roughly around 4,000 GPUs. And the other thing that's quite interesting is we have to have quite a bit of local caching storage to actually make that data available to our compute seamlessly. And so I'll talk more about that, and that's going to be the reason I also talk about rapids towards the end of this talk. So my main central point in this talk is that creating the right data sets is the cornerstone of today's machine learning. Whichever method you look at, whether it's traditional machine learning, like we've been doing it for a couple of decades now, or all the more recent advances around deep learning, building the right data sets is ultimately what solves your problem. So if you look at traditional software development, I think you typically have a cycle that looks like this. You write some initial code, you get some source code, then you use a compiler to turn that source code into an executable. You run that executable, you learn from it. You're going to run that executable, debug your code, and ultimately use that knowledge to improve the source code. And you go over that cycle over and over and over. And the industry has developed tons of tremendous tools to support that type of flow. So something like GitHub, code versioning, CI, Jenkins, all these tools basically give us an extremely solid foundation to essentially go through that cycle, develop initial code, rapidly compile it. Compilers are reproducible, they're deterministic, they spit out the same result twice. So traditional software development is very advanced. We've been investing in this for decades. Now you look at ML development, I'm drawing the analogy, and I think the process looks very similar, except there's been quite a few changes. So first, it starts with data. You typically always start with an initial data set. From that data set, you're going to use machine learning algorithms to essentially produce a predictor, whatever that predictor is doing. From that, you're going to learn about your current predictor, actually run it, and use it to learn about the mistakes you're making in the wild, and then use that to essentially improve your data set. And so it's really a very similar loop, right? You start with some data, you train a predictor, and so the mapping, I think, looks like that. The original source code is getting replaced by data. The compiler is essentially the body of algorithms we have. So deep learning, machine learning algorithms, I think it's really the right mental model to think of these as compilers. And so what you would expect from a compiler is that they're deterministic, and given one data set, they would spit out the same predictor. And the executable, of course, becomes a predictor. So when you look at the state of things in that flow, I think we've made a tremendous amount of progress on the upper right side, which is like data sets available. The industry as a whole has so much data available in so many industries today. And then on the algorithmic side of things, tremendous progress both on core machine learning algorithms, and more recently, over the past 5 years, an explosion of progress around deep learning and core deep learning research. So this is super exciting, and it's really what's driving and fueling the whole current excitement around AI. But I would argue that on the lower left side of that slide, I think we're really lagging behind. And it's actually really challenging to deploy these pipelines in industrial settings and use ML to actually solve problems and do it in a way that's systematic, reproducible, and really scalable. And so when you look at the problem of self-driving cars, it's really, again, like starting at the science level and quickly getting a prototype together is kind of straightforward. But then getting it to the next phase of actually scaling your data sets and hitting very specific targets of accuracy for all your models is a huge challenge. So I think one first step, in trying to address that problem is the general paradigm of active learning. And I'm using active learning quite loosely here. I'm using that to describe this general body of algorithms that aim at selecting data and improving them recursively over time to solve your task. So what is active learning exactly? So the general idea is that you start with some unlabeled data. And then you have a pool of labelers that can essentially augment that data with symbols like labels and whatever metadata you're interested in predicting from that data. You end up with some labeled data. With that labeled data, you can produce a trained model, your predictor. And then what you're going to be doing is using that pre-trained model to essentially predict an out-of-sample unlabeled data and measure your confidence on these predictions. And the more you can do that, the more you can essentially use your current best model and your current best labeled data to essentially discover new, most informative, unlabeled data to keep building up your data set. And I think that framework is incredibly general and a really strong foundation to help us turn the process of scaling machine learning development into something that's more deterministic and robust. So intuitively, why does all of this make sense? So if you have a training set, you train a model, and then you keep expanding your training set by adding random data, you're very quickly going to observe a curve like that. And I think all of you guys doing ML on a daily basis are going to be used to that type of curve. You know, it's easy at the beginning, it's very excited, and then you get to a point where you're reaching 99% accuracy, and your business really requires you to get to 99.999 to solve whatever problem you're trying to solve. And again, for self-driving cars, the targets are extremely high. And so when you switch to active learning, you have this lever, this mechanism to essentially get out of this plateau. Intuitively, that's the case because most of the data you're going to be sampling in the world is going to look like that, and your models are going to typically nail those cases very quickly, whereas this type of example is going to be much harder to solve. And one day it'll happen to you that there's this one guy doing that on the highway. And so the whole point of active learning is to discover these types of hard cases in large bodies of data and essentially direct our attention on things that need to be added to our training sets. So active learning is interesting. There's been some research around that. I think the community as a whole, across machine learning and deep learning is usually more interested in making progress on the algorithmic modeling side of things, and less so on the challenge of actually scaling data sets. And I think it's something that needs more attention. The one thing I'm going to be talking about today is how we started using that general paradigm to essentially drive our infrastructure work at Nvidia. So a couple of years ago, we started this project called maglev, which is essentially our internal production-grade machine learning infrastructure. And we've started this really to address the problem of how are we going to manage these data sets at such a scale, turn them into models, actually deploy these models in our car, make continuous improvements, test these models at scale, and do all of this at the scale of these tremendous data sets that we have to handle. And again, these data sets quickly exceed petabytes of labeled training and testing sets, and so it really makes the problem challenging. So in a nutshell, the platform looks like this. So there's really two components, and I'll spend a couple of minutes on that slide. The lower part of the slide shows you our internal cluster at Nvidia, so roughly 4,000 GPUs organized in DGX systems. So a lot of compute power. I think it's roughly 500 petaflops of FP16 power right there. Over that, we're basically running Kubernetes, and we've developed a whole bunch of services to essentially schedule jobs and track the progress of these jobs. So we're doing all sorts of things around tracking experiments, results over time, enabling the team to do things like hyper-optimization of our multiple models. So the cluster itself is quite busy. The second side of things that's really interesting is the data aspect of things. So because data is so central and you're dealing with such volumes, and you have to have the ability to essentially select relevant data, get it labeled, get it consumed in training jobs and validation jobs, the data management aspect of things is really a tremendous amount of work and complexity for us. And so typically, you start with data that's being uploaded from a car. The fun fact there is that because the data we collect in car is uncompressed, we're talking about terabytes of data generated per hour. And the only system we could find that has enough bandwidth to basically upload that data from a car to the cloud is FedEx. And so I'm telling you, FedEx is the highest bandwidth system out there. It's very low latency, but the bandwidth is tremendous. Once the data gets uploaded to the cloud, it ends up in a lake, and then we have these mechanisms to essentially apply pre-trained models to that data, select it, and then typically enqueue it for labeling jobs. So managing these 1,500 labelers is also quite a bit of a challenge. We have to have all this mechanism to essentially, we're treating them as consumers of a web application, and it's an interesting challenge of how do you prioritize work and projects, and how do you make sure that the data you select is relevant for the progress of the team. And once the data is labeled and available to the team, then it becomes a more systematic training and testing workflow. So one thing that's really key about this whole project is, again, the data management side of things. So we've organized this into a hierarchy of systems that starts from the big data management side of things, so essentially raw data being pushed to the cloud. And then multiple systems. We've started leveraging all sorts of open source engines, from Presto to Spark to Hive, to essentially query all the metadata we have available and assemble data sets. We're progressively correlating that to all sorts of third-party data sources, like mapping data, so that we can very quickly mine, say, scenes of that were taken next to a specific traffic light or things like that. Like the ability to essentially quickly discover data that's relevant to pre-build a training pipeline. And then the output of that is essentially feeding into our deep learning applications, and there we, as a company, Nvidia is building all sorts of tools to make that faster and more seamless. One library that we've developed is called DALI, that essentially help us maximize the throughput between disk and in GPU memory for streaming applications like deep learning. So because data is so central and we're dealing with data at that scale, and we've got to make sure that we consume it seamlessly in our compute jobs, we also had to spend quite a bit of time in the hierarchy of storage systems. So that's what we call data tiering. We're leveraging the cloud a lot because it lets us replicate data across multiple locations worldwide. So that's what we're showing on the left side, a bunch of services on AWS, data stored on S3. And then what we started doing is building a sort of optimized rack design that contains two things, CPU nodes and GPU nodes. And we're running SwiftStack, which is basically an open source S3-like API for storage on these CPU nodes. And then we basically use that system to replicate data that's useful from the cloud into that local storage. And then we have a caching system at the level of the GPU to essentially consume that data seamlessly into the nodes. So that tiering is really complex, and the more it goes, the more we want to be able to lower the distance between storage and compute. So what if we could push the data even closer to compute? So that's where Rapids comes in. Since data and applying compute to it for training and testing is such a central cornerstone of machine learning, it's really a problem that we have to solve. So at a high level, if you look at what's typically done today, there's a lot of back and forth movement of data between disk, host memory, and then GPU memory. And this, tiering levels makes the compute sometimes really tricky to optimize. And so the question is, what if we could keep data in GPU memory at all times? What if we could literally preload a few terabytes of data into GPU memory and then essentially define our whole pipeline from data preprocessing to feature extraction, ETL, all the way to model training, testing, and never leave the GPU memory. So that's really what defined Rapids and what we wanted to achieve with Rapids. So at a high level, we kind of built Rapids around the Apache Arrow data format. And the whole idea of Rapids became, what if we could essentially make Apache Arrow available in GPU memory and then build all sorts of libraries and interconnects to interface to tons of other libraries and the rest of the ecosystem. So we're showing you a few examples here. So from cuDF, which is essentially a CUDA-based data frame library that's essentially compatible with pandas, to cuML, which is our library of machine learning primitives covering the things you typically find in scikit-learn, and other machine learning libraries, to cuGraph, all sorts of graph primitives to manipulate data as graphs, and then connections to typical deep learning frameworks like PyTorch, Chainer, MXNet, and we're working on TensorFlow as well now. And so I think what's amazing about this idea is to look at the historical progress and what happened in the field. So back 10 years ago, we started doing we started thinking of how we're going to deal with data sets that don't fit in one node. And so Hadoop and MapReduce kind of like came in, and the general idea was we're going to set up this system where you can distribute jobs. Data is sitting on disk. And we're going to read it into host memory, do something with it, and then spit it back to disk. And so the first row typically shows you a typical pipeline happening on Hadoop, where you're going to query the data, do something, write it back, then load it again from disk, do the same thing again for ETL, sort the data set, group two data sets together, pivot them on one specific attribute, and then write them back. And then ultimately, you end up with some kind of training data. You read it again, you train your model, and you end up with a model. So in that system, the beautiful thing that Hadoop introduced is that you could distribute that heavily and deal with very large data sets and scale horizontally. But the challenge is you kept going back to disk. So then later, Spark came in and just really completely changed this. And the whole idea of Spark was, hey, what if we could skip the disk entirely, read things into CPU memory, and then keep doing that and never leave CPU memory? And so essentially remove all the bottlenecks to disk across the entire pipeline. So that really showed tremendous speed-ups, and Spark got adopted quite heavily in the industry. And so then I'm going to skip all the way down to what we're doing with Rapids. I think the analogy is we're doing what Spark did from disk to host memory, and we're trying to do that from host memory to GPU memory. And our whole model is load your data sets into N GPUs, and then never quit, never leave the GPU memory, and do all your compute in place. So we've shown tremendous benchmarks and results on that, and we're really excited to see more libraries and coverage being built around that. So in a nutshell, Rapids is essentially CUDA plus Python. Nothing, no magic. What we're doing is we're really taking all the primitives that you need across the entire spectrum of data science, from data frame, manipulating data sets, loading them from all sorts of third-party formats or other libraries into that core Arrow format, and then covering the space of machine learning primitives and ultimately connecting that to deep learning frameworks as well. And on top of that, Python bindings. The whole Rapids project is really Python native. We're really trying to embrace the fact that most of data science today is done in Python heavily. And so we want to start with that workflow that exists and essentially make it scalable. The way we're getting to multi-node is primarily through Dask. So we're really excited about that. We've hired Matt Rocklin, the author of Dask at Nvidia, and he's really helping us integrate and make these things work very tightly together. So the whole idea is to have deep native integration between PyData and Dask, and use Dask as a way to kind of natively scale out jobs across not only multiple GPUs, but multiple nodes and multiple GPUs across multiple nodes. And we believe that like this, we're going to create this environment where you can start from your plain Python code and very quickly do distributed ETL and ML jobs. So super excited about this. The last thing about Rapids is the inter-up. We really believe that it's critical for us to build something that can connect to all the third-party libraries out there. So we're making sure that we have bridges to libraries like PyTorch, MXNet, Chainer, and again, working with TensorFlow and this as well. The end goal really being that once you've loaded your data sets into memory and you manipulate them, you transform them, you sort them, you filter them, you don't have to write them back to disk. They stay there, and then you can pipe them into a PyTorch job, for instance. All right, so the code itself is available at rapids.ai. We also have pre-built containers that are available at ngc.nvidia.com, so you can literally fetch a Docker container and get started. And that's all I have for today. Thank you.
We have time for a few questions. There's one coming up, and okay.
So my question is regarding Rapid and GPMs. So will this work also with GPMs, with XGBoost or Light GPM?
Yeah, absolutely. In fact, the integration work in XGBoost specifically is already mostly done. And so for XGBoost, we're actually not replicating the work in QML, but we're just building integration with XGBoost and working directly in the XGBoost code base. And then we've got a public roadmap that kind of like shows the coverage of ML algorithms. Our end goal is, I think, by the end of the year to have covered most of 95% of the algorithms that are used out there. So not everything is done today, but our goal is to really map out everything that's used.
All right, let's. There's one. Oh, sorry, I missed it. Go ahead.
Maybe I missed that during the presentation, but machine learning models, they take a lot of memory, so it is hard enough to just feed them into the memory to begin with. So where do you have the space to store the rest of your data that you?
So for Rapid specifically?
Yes.
Yeah, so that's one challenge we're going to have to solve, right? So that's why we really think of this model where over time, one, we're going to have more GPU per memory, and then really max out, like progressively like improve the interconnect between GPUs. And so we really think that we can get this to work to a point where you'll be dealing with like 32, 64 GPUs, and look at that as one big GPU with potentially enough memory to deal with significant data sets and model parameters and so on.
Oh, I see. Thank you.
All right, let's thank Clément one more time.
Thank you.